So what we have here is a kinematics problem that we're going to have to split up into 3 different intervals to acquire the distance throughout the entire range. The problem states, a subway train starts from rest at a station and accelerates at a rate of 1.6 meters per second squared for 14 seconds. It runs at a constant speed for 70 seconds and slows down at a rate of 3.5 meters per second squared until it stops at the next station. And we want to find the total distance covered throughout those 3 elements. So what I've set up here is I set up a graph, a very subpar level graph, but it's showing what exactly is happening on the position versus time graph. So as time increases towards the right, the position changes. At first it accelerates, so it has a parabolic curve. And then in station number 2, the purple here, it reaches a constant velocity for 70 seconds, and then it starts to decelerate, which is the inverse of the parabolic curve there. So that's what's happening in this situation. And we want to take it step by step by step into 3 intervals here to solve the equation. So moving along here, we have our known and unknown. So I've created here a chart, another chart of what's going on. We want to separate it into stage 1, where we know the velocity initial was 0, the position here was 0, the time, this total time here was 14 seconds. That's a S, not a 5. And the acceleration 1 was 1.60 meters per second squared. We know in stage 2, all we know is the time to is 70 seconds. However, we can figure out these based on our information from 1. And step 3, we have acceleration was negative 3.50 meters per second squared. Now the question gives us acceleration as a positive number, but we got to remember it slows down, so it must be negative. Now moving forward, we have a bunch of unknowns, but those will clear up as we go. The equations we want to use are obviously the kinematic equations here, which you should be somewhat familiar with. And we'll start attacking this problem now. So the goal of this problem is to figure out the final x position of the subway train at each stage, so then we can add all 3 of them together. So let's start with stage 1. We know a lot of variables here. It should be an easy plug-in. We're going to use equation 1 here to get us started. So x final is what we're looking for. X initial is obviously 0. Velocity initial is also 0, which negates the change in time, which is 14 seconds, plus 1/2 the acceleration, which we were given to be 1.60 meters per second. 1.60 meters per second, and then the change in time once again was 14 squared. So a simple calculation there, it comes out to be equal to 156.8, and this is in meters. So now we actually have x, the final position here. You can fill that one in. So now we need to find the final position for stage 2. To do so, we're also going to use the same equation. However, we also need to find a new variable. If we look at equation 1, we have what we want to find, our x position. We can orient our coordinate system where the initial starting point of stage 2 would be 0, so we can just say that this is 0 to find this distance. Say 0 there, so x initial 0, but we need to find velocity initial. We can do that by using another kinematic equation and the information given to us for problem or stage 1. And then we have the rest of this. So what we'll use is this third equation here, because we want to find the final velocity of stage 1, which will be our initial velocity for stage 2. So to do so, we will write it out like this: velocity final, which is what we're looking for, equals, well, velocity initial in stage 1 was 0, so 0 plus the acceleration in stage 1, which was 1.6, times the change in time of stage 1, which is 14. This equates to 22.4 meters per second, which is our initial velocity for stage 2. So I just want to make sure that's clear. Our final velocity of stage 1 after the acceleration for 14 seconds turned out to be 22.4 meters per second, which is our initial velocity starting at stage 2. So now we can solve the final exposition of stage 2 with a simple kinematic equation of number 1 here. So this will be final position, which is what we're looking for, is equal to the final position here, which is, and then the starting point, we oriented the coordinate system, so it's 0 of x initial plus the 22.4 initial velocity times the change in time, which was 70 seconds for stage 2, plus 1/2 the acceleration, which is 0, times the change in time, which, since it's 0 there, it negates it. So our final exposition here turns out to be 1,568 meters. So now we have stage 2 completed, and all we're left with is stage 3. And what we do have, or what we do know, however, is that stage 3, the final velocity of stage 3, is 0. Okay? So, and we also know the final, or the initial velocity was 22.4, since there was no deceleration in stage 2. It stayed 22.4, it ended 22.4 meters per second. So since we have initial velocity and final velocity, we could solve this rather easily, which we'll be using the number 2 equation. So final velocity is 0, initial velocity is 22.4 squared in this equation, plus 2 times the deceleration of negative 3.5, change in x is what we're looking for, so let's solve. And I'll use a different color. So we got 0 is equal to the initial velocity, which is 22.4 squared, plus 2 times the acceleration, which in this case is a deceleration, and times the change in x. With some simple math, this comes out to change in x is equal to 71.68 meters. And we now have all 3 distances from each stage. So the final answer will be 71.68 plus 1568 plus 156.8 to give us a total of about 1,800 meters. I should make this an approximate, which is equal to 1.8 kilometers. So that was a fun problem where you had to set it up in all 3 stages. I hope you learned something.